Okay, here we're going to talk about Module 4B. We're going to talk about energy balances on closed systems and a little bit on problem-solving techniques. What we're going toward here is finding energy balance on things like piston-cylinder arrangements. Piston-cylinder allows for work to be taken out, and also because the boundary moves. Remember earlier we talked about the integral of PdV was the work out of the system, because the boundary is pushing back some force external to the system. And also heat can come in and out. So we have a closed system, meaning the mass stays in the system, but heat and work can come in or out of these systems. Okay, let's first look at piston-cylinder devices. Let's first look in the piston-cylinder devices at constant pressure situations. So we have a constant pressure expansion of the gas or the fluid in this system, and we're going to assume that this is adiabatic for starters. So assume we have adiabatic means Q equals to 0, and that's a word you're going to just want to have memorized. Adiabatic, no heat coming in or out of the system. And in this situation we're going to assume that P internal equals P external. In order for that to happen, we have to have this situation where there's no friction at the sides of the cylinder, and also it has to be done slowly enough so that the gas doesn't swirl around on itself and accelerate and cause friction internally due to the gas itself. So closed systems, adiabatic expansion of this piston is what we'll be doing. So now in this case the piston expanded in the cylinder and the gas pushed the piston up, so the work is out of the gas. If we take our system to be the gas itself, so the system being all, let's say, the gas in the piston, or the fluid in the fluid in the cylinder, then our energy balance will be on that fluid. So first of all, we'll have to figure out the work that was done, and recall that work is equal to the integral of PdV. So work integral of PdV. And if it's a constant pressure situation, as we defined here, then the pressure is constant. We can take it outside of the integral, and you have P, the integral of dV, which will give you P times V2 minus V1, and that'll give you your work. Recall, pressure times volume has the same units of force times distance, which is energy. Now we'll do the energy balance. N equals out plus accumulated. And look at what's going in. Nothing's going in. We assumed it was, first of all, adiabatic, so there's no heat going in. Since the gas is expanding, the piston is going up. The work is out of the system, or out of the gas. So 0 equals P times parentheses V2 minus V1. And the accumulated energy in the system is the mass times its change in internal energy. We're neglecting any changes in velocity of the gas in the system or any changes in elevation, and focusing only on the internal energy. So the mass times the change in internal energy will give us the total internal energy change, plus the work done, P times V2 minus V1, all that equals 0 from our energy balance. Now if we look at it, P times V2 minus V1, and replace that with MP times the specific volume change, then we'll be able to distribute the mass across this whole equation. And then if we have an ideal gas expanding, then it'll be M times P V2 minus V1 plus MCV T2 minus T1. Well, that's true for an ideal gas, where you have du equals CV dt, or delta U equals CV delta T per mass of gas. Okay, those are fairly easy problems to solve. When the pressure is constant, the integral is very easy. Take the pressure outside. Now what if the temperature is constant rather than the pressure? Now here we're looking at processes, so we're looking at what in the process is staying constant, or what is happening with the process. And in the process previously, let's go back, we had constant pressure process. So P was staying constant in this process. Now if we look at isothermal expansion, the temperature is staying constant. Iso means same, and isothermal would be same temperature. So here we have the work is equal to integral of P dV, work out of the system. And now to integrate P with respect to V, we have to have P in terms of V. So what I do here is substitute P is equal to nRT over V. You can solve that. P is equal to nRT over V. And you'll wind up with nRT dV over V is what you'll be integrating. Since T is constant, we can take it outside. R is constant. N is constant, so we have nRT, the integral of dV over V, and you see that's something fairly easy to integrate. So that equals nRT ln of V2 minus ln of V1, which you know from algebra is ln of V2 over V1. So take a moment, stop the video I recommend, and just convince yourself of that. Do that integration and see what you get. Okay, continuing on, we do the energy balance on that system. Recall we're looking at the system where the gas is expanding, but it's isothermal, so the temperature is constant. So if we apply our energy balance, N equals out plus accumulated, then we can calculate Q. Now, if the temperature is constant, then what will delta U be? Delta U, recall, for an ideal gas would be CV delta T. So if we take an ideal gas in this cylinder, CV delta T will be 0, and so you can't have any work unless you put some Q in. So this system is not adiabatic. This system has to have some Q going in, and in this case Q will be completely balanced by the work. So you have to put Q in, you'll get work out. MCV dt, or MCV delta T, will be 0. Because we call this an isothermal process. We're looking at an isothermal process. Now let's ask ourselves, if we look at isobaric compression. Earlier we looked at isobaric expansion. Remember, isobaric, baric being pressure, isobaric meaning constant pressure. And if we look at the compression, then we're lowering the volume. So the work in is equal to minus the work out. If you draw your arrow with the work going in, that's the negative of the work going out. So equals minus P dV, or minus P times V2 minus V1. In this case, when you're compressing the gas, V2 will be smaller than V1, so V2 minus V1 will be negative, times the negative P will give you a positive value for work in. So if you use minus the integral of P dV when you're compressing it, you should still come out with a positive number for the work done. Personally, I like to keep things positive, so I try to set up the problem with the arrow going in the direction where I think the work is going to occur. In this case, I'm drawing the arrow with the work going into the system, and so when I calculate the value, it should come out positive. If it doesn't come out positive when I calculate the work, then I know something's amiss and I may have had an error in my problem. All the time looking for ways to find errors. Okay, now let's ask, what if we have a mixture in there? Now we were talking about a gas earlier. Suppose now we have a saturated liquid and we start heating it up. Put Q in, so add heat. Put Q into that saturated liquid, what's going to happen? Now here I have it such that I have a piston resting on it with a constant pressure. So a piston's applying a constant pressure, which would be equal to the load on the piston plus the pressure of the atmosphere. And when I add heat to that saturated liquid, it's going to want to expand. It's going to want to boil. First thing it'll do once you start adding heat, if it's a saturated liquid, it's already saturated, so it's ready to boil. I add heat, it starts to boil, and the piston starts to rise. You start to produce vapor, and as the piston rises, it's pushing back the atmosphere, and it's pushing back whatever load you may have on the piston. and so that work is going out of the system. So we say it's doing work, or work is going out of the working fluid, which in this case, the working fluid is a liquid vapor mixture. Now if it's constant pressure, then it's fairly simple to calculate the work. Again, work is equal to the integral of P dV. Take P outside the integral, and so it's P times V2 minus V1, or P times M times V2 minus V1, where you use specific volumes there. And the specific volumes, you recall, we get from our knowledge of properties. If we do the energy balance on this, we have N equals out plus accumulated, and again Q equals W plus delta U. And so for example, let's take a 0.3 meter cube saturated liquid in a piston cylinder arrangement, and we'll heat it at constant pressure of 2 bars until half of it vaporizes. Find Q and W. That's the problem statement. Okay, so let's see. How much substance do we have to start with? The problem stated a volume, but when we're doing energy balances, and in general when we're looking at processes, we're going to be using mass to track our energies. Remember, in your tables, everything's listed per unit mass, so we need to calculate from the volume how much mass I have. So take 0.3 meters cubed divided by the volume in meters cubed per kilogram. 3 divided by 0.001061, and you get 283 kilograms in that 0.3 meters cubed. By the way, 0.3 meters cubed is about 300 liters, or exactly 300 liters. So we're close to just a little under 1 kilogram per liter would be the density, or a little over 1 liter per kilogram would be the specific volume. All right, so what's the final volume? We calculate that from our quality. We said that half of the mixture was vaporized, or half of the liquid was vaporized, so the final quality will be 0.5. So our volume of your mixture, you remember how to calculate that: 1 minus x times Vf plus x times Vg, and that'll give you your volume of the mixture in meters cubed per kilogram. Now you multiply that specific volume times your total mass that we calculated earlier, and you find that the final volume is 125 meters cubed. So it went from 0.3 meters cubed all the way to 125 meters cubed because the gas takes up so much more volume than the liquid. How much work did we do? Just calculate work is equal to the integral of P dV, or P the integral of dV since it's constant pressure, or P times V2 minus V1, which comes to, now I like to use, if I'm in metric units, I use kilopascals, because a kilopascal times a meter cubed will come out as a kilojoule. So you calculate that, fairly simple calculation, come up with 24,940 kilojoules for the work. Now you want to calculate the change in internal energy, and you have two properties to find that. You have, well, first of all, you have U1 is equal to the saturated liquid value of 504. U2, again, we use our quality. This is 1 minus x, UF plus x, UG, 1517 kilojoules per kilogram will be the final internal energy. The delta U then is the mass. The delta U capital is the mass times the specific change in U, and that comes out to 286 kilojoule, 286,000 kilojoules. Now you have the work calculated from the integral of P dV. You have the delta U calculated from the property data, and the question is, how much heat did you have to put in? So just apply your energy balance. N equals out plus accumulated. The work was out because it was expanding, and the gas was doing work against the load in the surroundings. And so Qn, W out plus delta U, and we can solve for Qn, is 311,450 kilojoules. So in order to produce 24,000 940 units of work, we had to put in 311,000 kilojoules of heat. And that's something, as engineers, we're always interested in. How much heat did I have to put in to generate a certain amount of work that I want to use for something? So here we go. Here's our working fluid guy. Got the fire under him, and he's pushing up the piston. Piston rises, does work, and you've turned that heat, part of it, actually not that much of it, but some of it you've turned into work, and that's one of our goals in thermo, is to produce work from heat. Work being good mechanical energy, and heat being thermal energy that's useful in some ways but not others, so we want to convert it to work often. Work, by the way, the unit's work can be converted from mechanical work to electrical work almost completely in an ideal system. Okay, if we look at this on a PV diagram, which is useful, we started here at the saturated liquid value, and we moved at constant pressure across to a higher volume. Actually, we go about halfway across in volume to 50% quality. Okay, now here's something I like to use for problem solving, and this is what I call a property process table. And we're going to get to problems later on where you have many states that you're going through in a process. You go from one state to another state to a third state to a fourth state. So I like to get organized. You recall, if you know two properties, you can find the third. So across the top I've indicated properties, and we have properties such as temperature, pressure, U, V, X. We could put H, S. Any specific property or any intensive property of the system we can put across in a row. In our columns, we have states of the process. So this is state 1, the initial state. After we expanded the gas, this is state 2, the final state. And the problem statement for the problem we just used was that it was a saturated liquid, so x equals 0 at the beginning, x equals 0.5 at the end, because I said half the mass was vaporized. So we went from a quality of 0, all liquid, to a quality of 0.5, all gas. Now what I've indicated here is that with these checks, is that if I put a check there, that means I know I can find that value. I'm not looking it up now, but I know I could find it because we have skills. Given two properties, we can find the third. Here are properties given where the pressure was 2 bars to start with, and the quality was 0. Since we know that half the gas expanded, that gives us a new property at the second state, x equals 0.5, and P equals 2 bars, because we said the process was isobaric, or constant pressure expansion. So this is a link between these two properties, and then this was in the problem statement that half of it was expanded. So knowing these two properties, P equals 2, x equals 0.5, we can find all the other properties, including the temperature. By the way, since it's saturated, the temperature would be the saturated temperature for 2 bars. Let's take a look at another example. 10 meter cube rigid tank is filled with saturated water vapor at 1 bar. The tank is cooled to 50 degrees C. How much heat is removed? Well, the first question we'd want to ask is how much work is done, I guess, because we're looking at closed systems. There are 3 things going on. There's a change in internal energy, there's a heat in or out, and there's a Q in or out. In a closed system, mass can't come in or out of the system, so we're only looking at the mass that stays in the system. We're looking at the heat interaction, and we're looking at the work interaction. So in this case, we know heat is added, but we ask ourselves, is there any work? Well, it's a closed system. It's also a rigid tank. So as a rigid tank, the boundary of the system can't move. So delta V is automatically 0. So there's absolutely no way there can be boundary work, because if the system won't move, it's not doing work to push back the atmosphere. There's another kind of work that we'll look at later called shaft work. But where you could actually take a shaft and put it into the system, put a mixer in there and put work in that way, but we don't have that here either. So we don't have boundary work, we don't have any kind of electrical connection or mechanical connection to the device, so no work, only Q. Set up our property process table and put in the specs of the system. We know that the pressure is 1 to start with. Let's see, 1 bar. And the quality is 1. We started with a saturated vapor. And so the internal energy and the volume could be calculated. At the end of the process, we know that V1 equals V2. So there's a relationship here between V1 and V2. Those two are equal, so that's what I call a process relationship. V1 equals V2, so I know that I have pressure here and quality here. I can calculate V. From that V1 I can get V2, and I was told that at the end of the process the temperature is 50, and so 50 temperature, V1 equals V2, so I know the volume and the temperature, which allows me to calculate the internal energy at the end. Again, this is a constant volume process, so V1 equals V2. I like to draw a little box around my process relationship sometimes so I can see that once I calculate V, filling in the numbers, V is equal to 1.694 at 1, also at 2, so you can see that I can calculate U. And U is, you were told that it U1 is a saturated vapor, so UG at 1 bar is 2506.1. And I can calculate V1 also. Given that V1 equals V2, you can use information from V1 and T, and you'll find out that it's a saturated mixture. You go about using the volume and the temperature to calculate the quality, and these are things that we've done in the first few weeks of this course. U, you can calculate from the quality. Once you calculate the quality, U comes up to 523. So now we know we have the table completely filled out and we can answer questions related to this problem. We'll use the energy balance to calculate Q that we had to put in. So N equals out plus accumulated. No work coming in. The heat is going out, so 0N equals Q out plus mass times delta U. Our Q equals mass times U1 minus U2, or minus delta U. In order to solve it, we have to know how much mass we had. Well, we knew the total volume was 10 meters cubed. Divide that by the specific volume and get 5.9 kilograms. The heat coming in is the heat going out. In this case, we're trying to cool the gas until it starts to condense. We're going to condense part of the gas, so we have to take heat out. Is M delta U, or 5.9 times 2506 minus 523. We wind up with having to remove 11,700 kilojoules for this problem. So we looked at energy balances on closed systems, tanks. We looked at a tank problem. We looked at a couple of piston cylinder problems, and we looked at the case where we had an ideal gas and the case where we had saturated mixtures. So what you should be able to do at this point is take any problem, tank problem, piston cylinder problem, ideal gas, non-ideal gas. Well, if you have tables for it, you could use steam tables, or you could use refrigerant tables, and be able to solve these problems. We looked at problem-solving techniques. We quickly sketched a PV diagram. It's a good idea to, when you're solving problems, to get your bearings on a PV diagram. We created a property process table, and we used the table with the energy balance to solve a problem. So this is a getting you to where you can solve many different types of problems. If they deal with a piston cylinder or a tank, you should be able to work that sort of thing. So that concludes Module 4B, and where we'll go from here would be moving mass in and out of the system, and it gets even more interesting at that point.